Okay, hello again, Ling 441. We're going to move on today from just talking about how to generate or calculate formant resonances, in particular for schwa, and talk about how we can kind of shift those formants around to get to different vowels in the vowel space. So there's two theories that are, well, there's two primary theories for how this works in articulatory phonetics. One of them is called the tube model, or the two-tube model, which is going to be a lot more similar to the sort of tube calculations we just did for schwa. And that's actually sort of or a more widely discussed sort of model when you actually go out to like talk to phoneticians at conferences and whatnot. It's more mathematical though, and I feel like we've had a fair amount of math at the moment. So we're going to use a slightly different theory here to kind of get our bearings in terms of how to understand this. It's called perturbation theory. This one is not as widely discussed, but I think it's sort of a lot, well, it's not sort of, it's a lot easier to understand intuitively, even though there are certain parts of it that are a bit tricky. However, it gives you some rules of thumb you can use in case you kind of get stuck in thinking about how all of this is supposed to work. So, like I said, it's a little bit tricky, so I'm going to present it to you in two different lectures. First of all, in this lecture from one perspective, and then I'm going to switch gears a little bit and show it to you from a slightly different perspective. And then hopefully in the process of that, it will start to become clear how it works. Without any further ado, like I say on this slide, it can be a little bit difficult to wrap your head around, but we'll look at it from a couple of different angles. But that's the goal, is to figure out how we get from sort of the articulatory properties of vowels to their acoustic properties in terms of their formants. Okay, so without any further ado, let's go back to where we left off last time, sort of setting the stage for how to create different formant values for different vowels. We start off with a complex periodic wave produced by voicing at the vocal folds. That has a fundamental frequency, and because it's complex, it's going to have multiple harmonics in that complex wave, right? So there will be a series of harmonics that have frequencies at integer multiples of the fundamental frequency, and they will pass or emerge from your vocal folds into your vocal tract from your glottis. The harmonics which match the resonant frequencies of the vocal tract will be amplified, and the harmonics which do not match those resonant frequencies will be damped. And we calculated in the basic case, if you just have an unperturbed or just smooth tube that's open at one end, how do you calculate the resonant frequencies for that particular tube if you have a vibrating glottis or some sort of vibrating sound source at one end? The resonant frequencies of that particular tube or any particular articulatory configuration are called formants, and we can see them nice and easily in a spectrogram. And what we're going to talk about today is that when you have different patterns of formant frequencies, you get different vowels. But just a reminder here of the way this kind of works. There's multiple harmonics coming into the tube or the vocal tract or whatever resonator you're playing around with. And some of them are going to match these formant frequencies or resonant frequencies. And when they do, they will be intensified or enhanced. And if they do not, they're going to be damped. And so the ones that become louder, you're going to see as darker stripes on the spectrogram, right? Okay. Let's go back to this articulatory story about how vowels are produced in your mouth. Hopefully this all rings a bell from 201 and 341 as well. So we know that vowels are articulated with characteristic tongue and lip shapes. So you could have a vowel like E, and it's typically described as a high front vowel. The reason is because those two properties are describing where the highest arch of the tongue is, at least in theory. That's what it's supposed to do. So this highest arch of the tongue is in a high position because it's pretty close to the roof of your mouth. It's also in a front position. It's a lot closer to your lips than to your glottis. So that's a high front vowel. You can shift that highest arch a little bit back for oo, and you get a high back vowel because this highest point is further back. For oo, as we know, we also round our lips, so that's a high back rounded vowel. E, you do not round your lips, you kind of spread them actually if you produce it in its canonical form. So it's an unrounded vowel. And then we can also talk about a low vowel like ah. So in a word like ha, we lower the sort of highest arch of the tongue to be next to our pharynx rather than to our palate. So this is a low back vowel because the whole tongue is lower and it's still back, even probably backer than an oo, right? At least in the articulatory sense, because you're almost touching your pharynx with it back here. As we normally produce it, is not rounded. A lot of Canadians produce a similar vowel, which is rounded, but we're not going to worry about that so much today, as long as you understand these basic principles. And so, yeah, this is without any sort of acoustic equipment at your disposal, like 100 years ago. This would be a good way, or at least a reasonably good way, of describing vowels. However, so there are these 4 articulatory parameters that, say, phoneticians like Daniel Jones used to use, and we still use when we're using the IPA to describe vowels. There's the height of the tongue when you're producing it. There's the front backness of the tongue. There's the rounding of the lips. And then there's also this kind of mysterious 4th dimension of tense laxness. It's mysterious like the 4th dimension in our spatial reality too, I guess. So maybe this describes like overall muscle tension when you're producing a vowel, or the amount of effort, what have you. Tense vowels tend to be a bit longer. Lax vowels tend to be a bit shorter. But in quality, they're usually fairly similar. And there's not that many languages that have this distinction. English is kind of an exception in that regard. Be that as it may, like I said, Daniel Jones came up with a whole system called the Cardinal Vowels system to sort of use these dimensions to describe different vowels, or to kind of provide a framework for describing where vowels fit into your articulatory space, as it were. So we had this cardinal vowel number 1, which was supposed to be the highest, frontest, unroundedest vowel that you could produce. And here's Daniel Jones trying to give it a go. Oops. Yeah, I'll play that again, because why not?
Number 1. E.
And then there was oo. We'll just kind of skip around here, but oo was the highest, backest, roundest vowel you could produce.
Number 8. Ooh.
And then ah was the lowest, backest, I guess, unroundedest vowel.
Ah.
And other than that, you're kind of going around the circle in what's supposed to be evenly spaced out articulatory positions. So this is going to go
number 1. E.
From high to low in equal steps, supposedly.
Number 2. E.
And maybe a little bit back or 2.
Number 3. E. Number 4. Ah.
Then you get over to the back part of the space and you just go from low to high in terms of your tongue position, right? And also switch lip rounding as you go too.
Number 5. Ah.
So now these are the back vowels, these are the rounded vowels, 6 through 8.
Number 6. Oh. Number 7. Oh. Number 8. Ooh.
And yeah, so like in the 60s or before then, you might get sent off into the field where you would have the opportunity to transcribe a language that nobody had ever heard before, or transcribed before for that matter. And in theory, you could use this sort of framework for saying, well, this language has like a vowel that's close to cardinal vowel 1, but maybe a bit more central, or maybe there's a vowel that's halfway in between cardinal vowel 7 and 6, but it's rounded and back, whatever you want to call that. And you kind of have to rely on your internal sense of where your articulators are as you're doing this, which is not super easy when you're producing vowels, because generally speaking, you're not making contact when you're producing them. Well, maybe you are, but not where it really counts, basically. So it turns out we can get to the same diagram in a different way, using technology that, again, was developed in World War II to kind of help communications on the battlefield back when it really counted. And then it turned out we could use it for other more fun activities like phonetics. So acoustically, vowels are primarily distinguished by their first 2 formant frequencies, their lowest resonances in terms of frequency, which we refer to as F1 and F2. So F1 corresponds to vowel height, and unfortunately, because we're sort of used to thinking about this in articulatory terms, or that's kind of the standard that was set before we realized that these distinctions are made acoustically, or how they're made acoustically, we get a kind of backwards labeling system here. So F1 will correspond to vowel height, So lower F1 corresponds to a higher vowel articulatorily, and a higher F1 corresponds to a lower vowel articulatorily. F2 corresponds to front backness. I've actually got a little diagram here I'm going to show you in a second. But F2, when you get a higher F2, it's a fronter vowel. When you get a lower F2, it's a backer vowel. So, yeah, got that question there. I've tried to draw this out on my whiteboard, which I haven't used at all. And we'll just give it a go. Hopefully you can see it. I'll find out later when I look at this video myself whether this makes any sense at all. But if you can see it, I've drawn it with the 2 dimensions here. So F1, if you plot out a vowel's acoustic resonances, F1 we will plot on the vertical dimension, but it's a little bit backwards because our 0 for F1 is going to be in the upper right corner rather than down in the lower left corner, the way it normally is when you plot out something graphically. And then this upper right corner will also be the 0 point for F2. So F2 will increase in this dimension, going from back to front. And this goes from high to low, which, like I said before, is kind of the opposite of what you might expect. I've also plotted in here some sample values for a speaker like me. So my F1 for schwa is about 500 hertz, and my F2 for schwa is 1500 hertz. And that's going to put me basically in the middle of my vowel space. So 500 is sort of halfway between high and low for F1, and then 1500 is going to be halfway between front and back. So you can kind of use that as a reference point for me, or speakers who have vocal tracts basically my length. And anything higher than F1500 for F2 would be a front vowel. Lower than that for F2 would be a back vowel. Anything lower than 500 for F1 for me would be a high vowel. And anything higher than that would be a low vowel, generally speaking. But schwa gives you kind of a reference point to be in the center of the space, and those particular values for a speaker like me gives you a reference point for me in particular. Like I said, though, your mileage may vary depending on how you actually produce these vowels in your space and the kind of mechanics you have to work with, depending on how long your vocal tract is and what resonances it produces because of that. Okay, so this kind of reiterates what I just said. This is me producing that exciting vowel, and these values work for a vocal tract length of 17.5 centimeters. The specific values you can measure for this particular vowel are these, so they're pretty close, but not exactly right on the button. So my vocal tract length might be a little bit shorter than 17.5 centimeters, but it's in the neighborhood. And like I said, in your exercise, you're going to figure out how long your vocal tract is, roughly speaking. You can do it with the magic of phonetics and mathematics. Okay, so why we care about this is that we want to know how we articulate these other vowels. So with schwa, you just kind of open up your mouth and phonate. You don't sort of push your tongue around in any obvious direction. You just and you get these formant frequencies. It's kind of what you get for free in this system. But we want to get to all 4 corners of the space, to sort of the perimeters of our articulatory possibilities, like Daniel Jones used to do. And so we want to know how we can push these formant frequencies in each of these 4 directions towards the 4 corners of the space. You guys are almost certainly too young to remember the 4 corners offense from basketball, because there's been a shot clock now for 40 years, but that was if you know what a 4 corners offense is for basketball, it's like that. We're going to pass the ball around the extremes of the space and just waste time. But we're going to learn things on the way, so it's not a complete loss. All right, so here's our first answer to this question. We're going to talk about perturbation theory. And then when we get through this, we're going to talk about the 2-tube model in a second, or in a couple of lectures from now. So the idea with perturbation theory is that it's based on the knowledge that the resonances of a resonating tube, or the resonant frequencies of a resonating tube, are kind of based on the standing waves we create in that resonating tube, and also the locations of the nodes and antinodes in that in those standing waves. So yeah, I just said that here. I probably could have just read through it, but this is just kind of lining things up here with what we know about the vocal tract and also what these standing waves are going to look like. So we can say this is our glottis here, which has a pressure antinode at all times, no matter what kind of standing wave you're dealing with, and the lips will always have a pressure node. So we kind of always get this pattern at the ends of the tube, and then when we go from the first resonance to the second resonance to the third resonance, we're just adding an extra kind of pair of node and antinode in there for each step up we take. And this is mathematical, right? So in theory, you can just keep on going up the scale to infinity. It turns out we really don't have to care about anything above the first two formant frequencies, although there is one case where we will look at F3. But beyond that, we don't care about F4, F5, F6, so on and so forth. They're there, but your mind doesn't care. Okay, so what's the big idea of perturbation theory? So this is a theory that was first espoused by a couple of Japanese phoneticians almost 80 years ago, named Chiba and Kajiyama, in a classic text on the subject. So they came up with this idea that formant frequencies can be changed by perturbing the airflow of the standing waves in the vocal tract. So the first part of this idea that we have to kind of use to set up the framework again is that the velocity of standing waves is inversely related to pressure at any point in the standing wave. And you can kind of think about this. I've borrowed a diagram from a textbook for this, but you can think about an air molecule oscillating in place as the sound wave passes through it. And when it's kind of far away from neighboring molecules, it can move relatively freely or maximally freely, so it moves at a relatively high rate of speed. When it starts to bump into other molecules next to it, though, it slows down, right? Because it just has to bump into something that won't get out of its way. So when it bumps into things or gets near to other things, there's more pressure. There are more molecules within a certain amount of space. So more pressure, less velocity. In the middle, there's less pressure because there's fewer molecules in its way, and you get high velocity. So there's basically this trade-off between velocity and pressure when we're looking at a standing wave. And it's sort of like the Bernoulli effect, but I don't want to talk about that too much lest it potentially confuse you. So remember, the reason I'm talking about this is because we kind of have to make a switch in how we represent these standing waves. So a vocal tract is a tube with one open end at the lips, and it's got a sound source here at the glottis end. And we've talked about the standing waves we produce in a vocal tract heretofore as pressure standing waves. So I just mentioned a couple of slides ago, we're always going to get a pressure node at the lips, no matter what resonance we're looking at in the vocal tract. And we're always going to get a pressure antinode at the glottis. But we're going to translate this to be the complete opposite because that's what Chiba and Kajiyama did. And since they were the geniuses who came up with this, we're just stuck with their formalism for it. So we're going to switch everything. We're going to flip everything on its head. And we're going to say anytime you get a pressure node, that turns into a velocity antinode. And that's what we see at the lips, no matter what. And then if there's a pressure antinode in the standing wave, that means there's a velocity node there. So a spot where velocity is basically never changing. And that's what we see at the glottis. Okay, so that's kind of step one for this. If you want to get a sense of how we're changing the diagrams, we can look at our two standing wave patterns for F1 and F2. These are plotted in basically a similar fashion to the way they appeared in Chiba and Kajiyama's initial text on this matter. So again, we have a node for velocity at the glottis. We have an antinode at the lips. That's supposed to translate, this V1 here is supposed to translate to the lips there. And unfortunately, I don't really have anything labeled here for the node because they're more focused on the antinodes. So for F2, you can see the lineup maybe a little bit easier because there's two of them. So here's our antinode at the lips for velocity, and here's our antinode basically somewhere in the pharynx. In the middle of this big loop here at the back of the standing wave. And then we'll see nodes for velocity sort of in the palatal region and also at the glottal region here too for F2. Okay, so that's our first leap of logic we have to make. Secondly, what happens when we perturb the tube or make constrictions at some point in our vocal tract. So the idea Chiba and Kajiyama came up with is that if you have a constriction at or near a velocity antinode, that's going to decrease the frequency. And it's a little bit hard to intuitively understand these ideas, but I'll take a shot at explaining it to you. With velocity antinodes, you're kind of flipping back and forth between high and low velocity, or basically velocity heading in different directions with, I don't know if you can say different vectors for that, but you go from high velocity to very low velocity at a particular point. So the idea is if you constrict there, you're kind of putting more pressure on that velocity antinode, and the extra pressure is going to slow things down. So if you slow down the velocity, that's going to decrease the frequency of whatever standing wave has a velocity antinode at that spot. So constriction at a velocity antinode decreases frequency. I'm going to write these concepts on the board as well before I start the second half of this lecture, and then we'll kind of review them before we get into some examples. The flip side of that is that if you constrict near a velocity node, that's supposed to increase frequency. And it might be a little bit easier to think about this in terms of the sort of counterpart of velocity here, thinking in terms of pressure. So a velocity node, wherever it is, it's basically a spot in the standing wave where velocity is not really changing. So if you constrict there, it doesn't really have the same effect on velocity that constricting in an antinode would, where you get sort of the maximum distinction in velocity. Instead, here you're getting the maximum sort of flip back and forth in pressure, where you either get high pressure or low pressure. And if you constrict there, you're kind of constricting the amount of space the wave has to operate in, and that will increase the pressure, or increase the pressure polarity, you might say, and without really changing the velocity so much. And so that is supposed to enhance airflow, as it were, and increase the frequency of the standing wave at that point. So there's two halves of this theory. One, if you constrict at an antinode for velocity, formant frequency goes down. If you constrict at a velocity node, formant frequency goes up. Okay, I'm going to add a caveat to this, because when we actually try to play this out in reality, you're not always constricting exactly at one of these spots, exactly at an antinode or a node, and it kind of depends. Like if you get in the neighborhood of one of these things, it still has an effect. It's a bit like horseshoes and the fact that being close counts. And the closer you are, kind of the more of an effect you wind up having. So yeah, here's the goal. Let's figure out how we can perturb the airflow in the articulatory tract to get to the corners of the vowel space, the four corners. Offense again. So to do this, we have to move in four different directions. So I'm going to try to show this on the slide and on my little board as well, but we want to move to a high front position, and our default is schwa, right? So to get to a high front position, we have to get higher F2 and lower F1. Similarly, if we want to go to a high back position, I just bonked myself in the face. If we want to go to a high back position, then we need to lower F1 and also lower F2, going from schwa as a starting point. If we want a low front vowel, we have to kind of go in the opposite direction that we just did and raise both formant frequencies, raise F1, raise F2. And if we want to go low back, we need to raise F1 and lower F2, right? So we can sort of tweak each of these formant frequencies independently of each other, although there is some interaction. And the main thing is, though, that we have mechanisms in place, given what we've already learned about nodes and antinodes in the vocal tract, to enable us to produce all four of these types of articulations, to get all four of these acoustic effects. So I want us to consider each one of these in turn, and I'm going to just walk you through the framework more explicitly here before looking at the specific examples. So with F1, we have a velocity node at the glottis, velocity antinode at the lips. Remember, to lower F1, to lower this formant frequency, we constrict at or near an antinode. So the best option there would be constrict here or reasonably anywhere close to the lips. That will lower your F1. And if we want to have the opposite acoustic effect, we want to make a constriction over here at the glottis or somewhere close to it rather than closer to the lips. That's how you move F1 around. Similarly for F2, well, what's different about F2 is we have both two nodes and two antinodes, so that makes it kind of more interesting. But for F2, we have nodes at the palate and the glottis, and then we have antinodes at the lips and the pharynx, more or less. So what happens when we make constrictions? To raise F2, we want to constrict at these velocity nodes, the palate and the glottis, here and here. And to lower F2, we want to constrict at these antinodes, at the lips and the pharynx. So that is basically our framework. And I'm going to write that down on the board. I'm going to pause the video for now and then pick it up in a second half. But hopefully you understand that as it is. When I do this live in class, normally I'm writing all this stuff on the board so we can keep track of the record. That's why I'm writing it on the whiteboard today as well. So I guess I would say if you don't feel like you're comfortable yet with this, before we go to the examples, maybe review the video and walk through the steps again. And I would also recommend writing down the mechanics of this system, like what we do to raise F1 or lower F2 or what have you. And then we'll hopefully start making a little more sense, because that's what I'm going to do right now anyways. So we'll be on the same page by the time we start the second half. Okay, see you then.